G'day, I'm Braden Haskett. Myself and my teammate Jack Walsh will be explaining to you in this presentation the findings of our feasibility study on the Clyde ore body. Let's cut to the chase and start with an economic analysis. The first thing we're going to look at is the total revenue from the mining method over the life of the mine. You can see here off the bat, the modified Evoca method and the narrow bottom-up method make about $80 million in profit, where the bulk bottom-up method makes $120 million in profit by the end of the life of mine. The development costs are slightly higher in the Evoca method, where they're identical for the bottom-up method. Every mining method here has to use a tailings dam. The operating cost for the mine is obviously higher with the bulk methods versus the narrow method. They have similar infrastructure expenditures, and the post-mining costs are similar for the bulk methods and then lower for the narrow method. And the income likewise is higher for the bulk methods and lower for the narrow method. So here, just off the bat, we're going to be leaning towards a bottom-up mining method because it has less complexity than the Evoca method, but in some cases here with the bulk method, it's making more profit. So off the bat here, you can pretty much eliminate Evoca for this ore body. NSR is an important indicator in this case because it's essentially telling us how profitable it is to sell the ore once it's in a state that has it ready to be sold. So we want to look for the highest NSR. That's basically the most efficient ore to sell. We can see here the narrow, obviously, because it's more selective, has the highest NSR, where the bulk method for bottom up, it's trailing behind, but not by that much, considering there's pretty much twice the amount of ore. This is pretty good for the bulk method. And here, Evoca, it's trailing behind. This is another point against the Evoca mining method for this ore body. Here we have a table of the cutoff grade. Essentially what cutoff grade looks at is how profitable it is to actually get the ore out of the ground and to the surface in a state where it can be, or to a state where it can be then transported off-site. What we're looking for here is the lowest cutoff grade. That would mean you have more resistance to volatility with a lower cutoff grade, because that means you can keep mining a more diluted ore than you otherwise could with a higher cutoff grade. So this would give us wiggle room against stuff like geological uncertainty. We can see here both the bulk mining methods have a lower cutoff grade compared to the selective narrow vein option. So this is a point for Evoca, but you can see that the bulk, bottom-up bulk option has been pretty good in all three of these measures. So that's why for the rest of the mine design, we decided to go ahead with the bottom-up bulk CRF-based mine design. In this slide, we have a breakdown of the cost and income by month for the life of the mine. You can see here in the first 6 months, there is no income coming into the project. It is all expenses for the first 6 months. Then between month 7 and month 11, we begin developing within the ore body while we're developing our ore drives. So we're getting a big kick of income here as we pretty much go on a development run that brings in a lot of income and creates this spike here. As you'll see later on, there's a big run of development in Q2 and Q3 of the first year, which is responsible for this spike here. Then beginning in month 12, all of our development's done and we're just doing our regular stoping cycle. Here you can see we've got a steady stream of income and expenses that continues until month 39. And by that point, we're at the top level, which has a slightly smaller stope. And then that creates a little drop down in income and expenses. And then that lower income continues until level 1 is extracted and the life of mine is completed. In this slide, we have a breakdown of the net profit against time. So you can see between month 1 and month 10, we're in the negative. So we get to a peak of $20 million spent by month 8, And then after month 8, we start making income again. And by month 11, we actually hit our break-even point and we make a slight profit in month 11. Then after that, it's a steady stream of profits until the end of the life of mine. You can see roughly $120 million in profit by the end. So beyond month 11, any investor in this project should expect to see a return on investment.
Moving on to our trucking requirements. So, since the processing plant is limited to 1,000 tonnes of ore per day, mining at the fastest rate possible isn't necessarily the best option. Thus, our mine production is at the same rate of the processing plant, so 1,000 tonnes per day or 41.6 tonnes per hour. The CAT AD45 trucks have a payload capacity of 45 tonnes and have a tipping cycle time of 36 seconds. So, bogging at 1,000 tonnes a day, the 41.6 tonnes an hour, the truck can be loaded at 55 minutes. After researching a safe travel speed, travelling underground at 30 kilometres an hour max is found safe, and 50 kilometres an hour on the surface is safe. So, using those speeds, and then the maximum longest distance is just under 2.5 kilometres. The longest cycle time for the truck to go from the bottom level all the way to the ROM and back is about just over 1 hour, 61 minutes. So thus the number of trucks we will need per production stope is essentially equal to 1 an hour, or just 1 in general. The TKM ranges dramatically depending on the haulage distance, as it's tonnes per kilometre, obviously. So as expected, because we're a bottom-up method, the TKM at the start will be quite low relative to what we'll end with. So at the start, it'll be at the start of level 5, it'll be about 17.9 tonnes per kilometre at the worst. And at the top, level 1 will have the best TKM of 48.05 tonnes per kilometre. So from year 1 to year 3, there's a 50% increase in the TKM, but the biggest difference is seen from year 1 to year 4 with almost a 100% increase, or doubling the TKM. The ventilation requirements of our mine is created by the total kilowatts of power operating at once underground. So we've assumed 1 bogger, 5 trucks at worst, which is a bit of an overestimation, 1 Charmac rig, 2 ITs, the Volvo L120 models, and this comes to a total of 2,957 kilowatts of power. So, putting that into the formula, Q equals 0.09 times the kilowatt, in this case 2,957, we get a ventilation requirement of 266 meters cubed to the face. So, the fan we have chosen to go through Minetech to get our primary fan. Is a custom fan which will be built similar to the specifications at the Agnew mine, and that has a target ventilation of 275 meters cubed, and it also has a 900 kilowatt output power. Since we're already getting Minetech in to do our primary fan, it'll be best to get them to do our primary booster fans as well. So those will be 1.7 meter diameter booster fan, which will provide 90 meters cubed of air and at 280 kilowatts each. The additional infrastructure that we are required to put in our mine includes of pumps, an escapeway, and refuge chambers. So, for the escapeway, we have decided to create a separate escapeway, not putting it in the return airway because that's that's not the best practice, but we also are using the decline to provide fresh air. If we were using a shaft to provide the fresh air, we'd place the escapeway in that fresh air source, but we are not, so we are creating a separate escapeway. So we've decided to use a safe product in case of an emergency in an attempt to preserve all human life in the mine. That is why we have decided to use the SafeScape system. It is corrosion resistant, rust proof. It's made of a durable plastic which can absorb shock and stay put in tough ground conditions. And the main feature, it has a static line. So if the workers fall, they won't plummet to their death, knocking other workers escaping. The line will grab them and keep them contained and make sure they won't fall. So it is an affordable choice, and we are going to use that in the escapeway. For the pump, both in the sump and the backfill drive, we have decided to go with a standalone true flow underground electric pump that will be custom made to suit our mining conditions and our requirements. Using the 200mm discharge pipe that we have been given, we can create a max flow rate of 167.5 meters cubed an hour using that true flow pump, using a 90% pump efficiency. If there was a choice of a 250mm pipe, we could almost double the output of water at 290 meters cubed an hour, but this would be pretty overkill. It'd be only used on level 5. So, the refuge room. The refuge room is a key part of infrastructure that will be located in our mine in case of an emergency. It is placed strategically so it isn't prone to flooding. We have decided to choose the MS SD4 12 SIV36 model of the mine safe refuge chambers, and these can hold up to 12 people safely. We have decided to choose 12 people because in case we're working 2 stopes on one level, we'll have enough room to fit 2 crews in. The refuge room is 4.8 meters long, allowing enough room so that the door can swing open without going into the access and potentially hitting vehicles or hitting people and that sort of stuff. The room is 6 meters high and 5.5 meters wide.
Thanks, Jack. I'm now going to round off the presentation with a quick look at the mine schedule. On this slide, we just have a quick breakdown of mine schedule by quarter. You can see in quarter 1, we develop our drift all the way down to level 1 access. We develop the level 1 access, and then we begin raise boring our escapeway and our RAW. For quarter 2, the decline is continued beyond level 4. The level 2 and 3 level accesses are completed, and then raise boring between those levels is also completed. Quarter 3 is another big one, just like level 2 for development. So we develop the decline all the way down to level 5. We finish off the level accesses to level 4 and 5. And then we begin developing our ore drive. So we actually smash out ore drives all the way from level 5 to level 3 in quarter 3. And we're again raise boring between each of our levels that have just been developed. Quarter 4 will see us finishing off our ore drives for level 2 and level 1, and then we actually take our first 3 stopes in quarter 4. From that point on, stoping will continue as normal, taking about 3 to 4 stopes per quarter for the rest of the life of mine. You can see here the life of mine runs just under 4 years for the entire project. This slide shows the calculations for our stoping cycle. I guess the main important number to look at here is the duration for the entire cycle. So it will take 50 days to complete an entire stope. Aside from that, up here, we have all of our calculations to come up with these numbers. It's important to note here, this is our maximum bogging rate. It's 1,300 tons per day. We actually didn't use that value to come up with these numbers. We capped that at 1,000 tons per day. That was to cap our bogging rate to the plant throughput. That simplifies our scheduling process, and it saves us the hassle of trying to deal with the mismatch of the plant throughput and our actual peak bogging rate. It also gives us a bit of wiggle room for unexpected delays that weren't otherwise accounted for. Now I'm just going to quickly walk you through, using screenshots from Deswik, the schedule from each quarter of the mine. In quarter one, you can see we're developing our decline down to level 1. We develop the entire level 1 access, and we begin raise boring up to the surface for our RAW and for our escapeway. In quarter two, we make a lot of progress, as I mentioned before, on our development. The RAW and escapeway finishes up in early Q2, and we develop our decline with one jumbo all the way past level 4. And with the second jumbo, we're developing the level access for level 2 and level 3. Quarter 3, we develop the decline all the way to the bottom, and then that jumbo that's been developing the decline the whole time continues on and develops level access 5. The other jumbo develops level access 4, and then they continue to develop ore drives 5, 4, and 3. Quarter 4, we finish off our ore drives. We take ore drives 2 and 1, and we actually get to take 3 stopes. You can see here we're taking 2 stopes at any given time on alternate sides. By the end of year 2, we're almost finished level 2. And by the end of year 3, we're almost finished level 3. You can see just before the end of quarter 16 or year 4, just before the end of year 4, we're finished taking all of our stopes and the life of mine is completed. Stoping activities. So this is a breakdown of the 2 concurrent stopes that are being developed at any given time. You can see here we've scheduled it in such a way that upper level activities and lower level activities are not going on at the same time. So there'll only be one level, there will only be one activity on any given level at one point in time. So you can see we have upper level activity here, lower level activity versus an upper level activity for each of our processes. So an upper level activity here with backfilling, and then a lower level activity with bogging. These are taking place on different sides of the ore drive, of course. This entire progress here of taking the 2 stopes at one time takes 63 days. So for our entirety of production, it's these 63-day steps where we take 2 stopes in those 63 days, going on in sequence until we take all of our stopes. What you've been waiting for, the final decision on this feasibility study. From these calculations, we would recommend that mining proceeds using the bottom-up CRF method. We would recommend that any mine operator would have at least 40 million in capital before starting the project. Our peak negative position only got to 20 million, but we would feel that it'd be irresponsible to start with only 20 million because there are always unforeseen circumstances and things that you just can't account for. After our break-even point in month 11, the mine will eventually provide $120 million in profit by the end of the 4 years. And that 120 million, it's important to note, is pretty steady throughout that 4 years. After month 11, production is very steady. Mining of the ore body will be utilizing rockfill and CRF in combination to backfill the stopes once extracted. And after the ore is processed, the tailings of that processing will be sent to a tailings dam, which will be located on site and cost about $15 million over the course of the project. Thank you for your time. We hope that these numbers speak for themselves and that your continued interest in the development of the Clyde ore body will reap you rewards in the future. Thanks again.